My name is Lewis McIntyre. I have developed a model for special theory of relativity that I call the velocity triangle that allows all relative problems to be solved on a simple polar plot. So let's get into it. This video will show you how to use the polar plot for a variety of Lorentz transform problems. You can download a copy of the plot on the link shown and follow along if you like. First, we're going to introduce what I call the velocity triangle and the trigonometric form of the Lorentz transform and Doppler shift derived from it. The triangle OAB, shown on the right, is based on the fact that all matter moves with a proper velocity equal to the speed of light, defining the direction of that travel as time. Relative velocity disappears as an independent variable, becoming a projection of one body's proper velocity onto the temporal axis OB and spatial axis BC of another body moving in a different direction. For BC equal to velocity times time in S1, which is also equal to BA, this defines the difference of direction, the angle beta, between reference frames S1 and S0. The sine of beta equals V over C. This allows the Lorentz transform and Doppler shift to be written trigonometrically as shown. The Lorentz transform simply equates the measurement x0 and ct0 in one reference frame to a measurement as observed in another, x1 and ct1. Next, I'm going to introduce the relativistic polar plot and show you how to use it. Again, you can download a copy of the plot at the link shown. This is the polar plot. The plot consists of radial lines at 7.5-degree intervals. The angles measured from the 0-degree vertical equal the arc sine of V over C with respect to the 0-degree radial. This is overlaid with concentric circles mapping out equal units of time and distance from the center, with time multiplied by the speed of light. A Cartesian grid overlays this for ease in computing time and distance. This plot allows the solution of Lorentz transform problems with compass and straight edge, no calculations necessary. Since this solution does not alter the orthogonality or units of measure of either reference frame, multiple reference frames can be solved on the same plot. To use this plot, let's establish the S1 reference frame time axis on the 0-degree radial. It's not necessary to use this radial, but it simplifies calculating the other angles. Time is measured from the origin at O. If the units of time were to be in seconds, then each unit of distance would correspond to light seconds, 186,000 miles or 300,000 kilometers. Next, we add the S1 x-axis at right angles to the time axis, and distance, like time, is measured from O. We must now determine the velocity angle for the problem we are going to solve. The other reference frame, S0, is opening to the right from S1 at half the speed of light. Half the speed of light corresponds to the 30-degree radial line. So that's where we put the CT0 axis and its X0 axis normal to it. Note that neither reference frame is distorted with respect to each other, but simply rotated. We want to solve the Lorentz transform of an event in S0 to its corresponding measurement in S1. What's an event? An event is the special case of a measurement consisting of proper time only with no X component in its own reference frame. We locate our event A at 5 units of time and 0 units of distance in S0. We use a triangle as the symbol for events. Before S1 can assign coordinates to its measurement of event A, it must first observe it. That is, light must be transmitted at time A to its time of observation in S1. To determine the time of observation, first we proceed along the spatial axis of S0 to intercept the time axis of S1 at B. Then an equal distance along the S1 time axis to locate the time of observation at C. Since the time of observation is also proper in S1, we again use a triangle as its symbol. The interval OB is the time of the event OA divided by the cosine of beta. AB is equal to OA times the tangent of beta. The time of observation is thus equal to OB plus BC, which is BA, which is geometrically, trigonometrically, the Doppler shift of OA to the time of observation, OC. The Doppler shift is also equal to the sum of the Lorentz transform of A, which is CT0 over the cosine for time, and CT0 times the sine over cosine for X. How does S1 assign coordinates to its measurement based on its time of observation? There are several ways in which this can be done, all of which give the same answer. But the easiest to understand is the concept of a ruler made of fixed points in S1. A moving body is at a fixed point D on the ruler when light from the moving body's event A arrives simultaneously with light from D, which is the Lorentz transform of A. The distance BD must equal the interval BC so that C equals CT1 plus X1, satisfying the speed of light between S1's measurement and observation. Since this measurement includes an X component as well as time, it's not proper, and we use a circle as its symbol. I call the circle centered on B the inferential circle, as it contains the event A, the observation C, and the measurement D. It also intersects its own time axis at CT1 minus X1, which is the time S1 must initiate an active measurement, such as by radar, to locate S0 at D. But why does light appear to propagate differently from a moving body along the path ABC versus from a fixed point along the path DBC? The answer is that light propagates exactly the same from both points, but not in a straight line, but as an expanding four-dimensional sphere. After light is emitted from A, it propagates at the speed of light in all directions, remaining centered on its emitter, which is also propagating in the speed of light in its direction of time. Light continues expanding until it intercepts the observer at C. Similarly, light emitted from D at CT1 remains centered on its emitter, as that emitter propagates in its direction of time. The expanding light sphere reaches C simultaneously with light from A. Thus, ABC is located on the bisector of the angle CEA and is not the path light took to reach C. It's just a convenient graphic solution that locates C with respect to A. We just demonstrated the measurement of a proper event with no X component. Now we're going to generalize this to the transformation of a measurement with an arbitrary X component. We begin by locating the measurement A in S0 at time 5 as before, but this time with X equal to 2, marking it with a circular symbol to indicate that it is a measurement. We are going to solve this graphically using an axis of symmetry for the Lorentz transform discussed in my book, Writing on a Light Beam, which has the derivation and proof. I'm just going to give you the cookbook solution here. First, you erect a temporary x-axis in the target reference frame S1 at CT1 equal to CT0, which is 5. From A, we proceed in the direction of S0's time axis to intercept the temporary x-axis at B. Then that same distance in the direction of S1's time axis to locate S1's measurement at C, which you can verify is the Lorentz transform of the measurement in S0. 5, 2 transforms as 5 plus 1 over the cosine of beta, which is 0.866, and X transforms as 2 plus 2.5, also over the cosine of beta. Let's see how Doppler shift affects the communication of this measurement to S1. S0 cannot communicate the measurement of A until it observes that measurement at A prime equal to the sum of CT0 and X0. S0 then transmits that measurement to S1, Doppler shifted along the path A prime, B prime, C prime, to the time of S1's observation at C prime. We rearranged the Doppler shift of CT0 and X0 to show that it is also the sum of the Lorentz transform of CT0 and X0. This is simultaneous with light received from the Lorentz transform of CT0 and X0 at C. Both S0 and S1 measure the same speed of light from their measurement to the observation, unaffected by velocities, which is the constraint from which the Lorentz transform was derived. Now we're going to show one of the most powerful and unique capabilities of the relativistic polar plot. That is, its ability to display multiple reference frames on the same plot because it does not distort the orthogonality or units of measure of any of the reference frames. We are going to begin with a proper event in S0 at time 2 with x equal to 0 to keep all of the solutions on the chart because we're going to be using some pretty high velocities. This transforms to a measurement A1 in S1 with beta equal to 30 degrees or 0.5 C as before. As we will have multiple betas on this problem, it's subscripted to identify its two associated reference frames, in this case, 1 and 0. Now we introduce a third reference frame, receding to the left of S1 with beta equal to 30 degrees, negative 30 degrees, making beta between S2 and S0 equal to 60. Their relative velocity is equal to 86% of the speed of light. What happened to the law of additive velocities? Adding 30 degrees and 30 degrees does not compute. Certainly not, but the law of additive velocities is derived by taking the Lorentz transform of A1, which is in turn the Lorentz transform of A0, and transforming that again into S2 as A prime 2. Dividing the resulting X2 by CT2 yields the velocity at between S2 and S0 at 80% of the speed of light, which is the additive velocity result for two relative velocities of half the speed of light each. The previous measurement of S0 by S2 was the result of direct observation of S0 by S2, and S1 played no intermediate role. Next, we add S3, receding to the left at negative 45 degrees with respect to S1, 75 degrees or 96% of the speed of light with respect to S0. And as V tends toward C, the Doppler shift and time of observation tend toward infinity. No observer can directly measure the event's clock. The observer can determine the proper time of the event by subtracting the square of its distance from the square of its time. Alternatively, the event may communicate its time of transmission In either case, the observer will get the same answer and conclude that the event's clock is running slow, being earlier than its measurement. In fact, it is the observer's measurement that is delayed by Doppler shift. We have all heard it said over and over that clocks slow down, or as we have shown, appear to do so, as relative velocity approaches the speed of light. This is true in the case of receding velocities, as we just showed. However, what happens when the bodies are approaching O, the time of collocation, which we have taken as time zero? Approaching bodies have negative time and up Doppler versus positive time and the down Doppler for receding bodies. Let's relocate event A0 at CT0 minus 2. Since the CT and X components of all of the measurements are directly proportional to CT0, they will have the same value as in the preceding case, but with negative sign. And because their absolute values are greater, but with negative sign, they are now earlier, more negative in time than the event. Thus, the observer will believe that the event clock is running faster than the observer's measurement. This does not violate causality, as the time of observation is always in the direction of positive time, whether receding or approaching, as shown for S1. This is because the time of observation is CT0 plus the absolute value of X, whether to the right or left matters not. Thus, the time of observation will always be later in time than the event, preserving causality. The time of observation becomes later with increasing velocity with S2, asymptotically approaching zero as velocity tends toward the speed of light, as in S3. This is because the time of observation is equal to CT plus the absolute value of X, and X is the speed times time, which as that goes towards C, X approaches the value of CT. So in conclusion, the relativistic polar plot is a powerful and easy to use tool that permits the solution of a variety of relativity problems, including mass, momentum, energy, and kinematics. It also reflects the underlying mechanism of the Lorentz transform in the special theory, showing that it is not the time and space of the event affected by its relative velocity with the observer, but the observer's measurement of the event caused by Doppler shift. And like Doppler shift, the event's measurement of the observer is likewise affected by Doppler. Please visit my website to download a copy of the polar plot and a simple tutorial for its use. You may also order copies of my book for these and many other problems solved with the polar plot. And I thank you very much for your time in listening to this. I hope you enjoyed it, and thank you again.